Hello, this is Miss Moore, and today during chemistry we're going to discuss mass to mole conversions. Today's essential question: how is the number of moles of a molecule calculated from the mass? For today's lecture, make sure you have handy both your periodic table and your calculators. Let's start with the question, what is a mole? So knowing the mass of a single atom or molecule is really not very practical because atoms and molecules are so small. It's very difficult or almost impossible to actually even work with a single atom or molecule. So in the real world, we deal with many hundreds and thousands of molecules at a time. So scientists came up with this new unit called the mole to describe a large quantity of atoms or molecules. So a mole is 6.022 times 10 to the 23rd atoms or molecules. Next, molar mass. One more time, because it's ever so important. A mole is 6.022 times 10 to the 23rd molecules. Then we've got this thing, molar mass. The molar mass is the mass of 1 mole of a substance, or the mass of 6.022 times 10 to the 23rd atoms or molecules, or actually anything. All right, so here's the cool part. It turns out that the molar mass of an atom is actually the exact same as its average atomic mass. That's the number found on the periodic table. The only difference is that the unit is in grams. Remembering that average atomic mass, the unit is AMU. Okay, so while one atom of, let's say, hydrogen, its mass is 1.01 AMU, if we had a mole of hydrogens, or 6.022 times 10 to the 23rd hydrogens, so a big old pile of hydrogens, that would weigh 1.01 grams. All right? And the molar mass of a compound or molecule is the same as its formula mass, but again with the units grams. So if you remember to calculate the formula mass, we look at a formula for a compound or a molecule, and we add up the masses of all the atoms that it's made up of, and to get the molar mass of that, you just add the units grams. Okay, mass to mole conversions. This is sort of the what's the point slide. So it turns out that practical, or maybe you could think of it as applied chemistry, is a lot like cooking. Okay, so scientists take so much of this atom or molecule and mix it in with so much of that atom or molecule, and they come up making so much of something else. Just like if you were to bake a cake from a box mix, you might need 2 eggs, and you mix to that 1 box of cake mix and maybe 1 cup of water, and you mix it all up, and you end up with 1 cake. Same idea. Okay, so we have this thing called the mole. And it's a really handy-dandy unit because it tells us both the mass of something and the amount of something. We know the amount of a mole is 6.022 times 10 to the 23rd, and we know the mass of a single atom, 1 mole of a single atom, I should say, what type of atom, is the same as the average atomic mass, except for with the unit grams. And we could also, from there, we know that 1 mole of a molecular compound, we could figure out the mass of that, okay? So using mole conversions, honestly, scientists really do use them. Scientists can figure out how much of something to use to make a certain amount of something else. So believe it or not, mole conversions are actually quite handy. Okay, the moment we've all been waiting for, the steps for mass mole conversions, how to do these things. All right, so we're going to be using the equality. 1 mole of something equals the molar mass of something. So a real quick review. What do I mean by an equality? Equality isn't a conversion factor, something to use, a true statement, this equals that we can use to convert from one unit to the other. One I'm sure you guys are all familiar with is like 1 foot equals 12 inches. That is a true statement. That is an equality. Okay, so again, our equality is 1 mole of blank or something equals the molar mass of blank or something. Why do we have those blanks? Well, because the molar mass is dependent on on what it is we're talking about. For a quick example, we could have 1 mole of hydrogen. We know that that is 1.01 grams of hydrogen. Whereas if we had 1 mole or 6.022 times 10 to the 23rd atoms of chlorine, we know that its molar mass would then be 35.45 grams of chlorine. By the way, I got both of these off the periodic table. Those are the average atomic masses, but written in grams. Also, we could have 1 mole of hydrogen chloride, and that would have a molar mass of 36.46 grams of hydrogen chloride. So again, the blanks here are what atom or what molecular compound we're talking about. All right, so as we're going through the steps for mass mole conversions, we are going to be calculating this practice problem right here. How many moles of CaNO3 or calcium nitrate are in 243.67 grams? So why don't you jot that practice problem down? So the first step is to rewrite the problem as a math problem. This is going to become more important as we go through the semester and our problems get more difficult. So again, our practice problem is how many moles of CaNO3 are there in 243.67 grams. So what we know is that we have 243.67 grams of CaNO3, and what we're looking for is how many, that would be our x moles of CaNO3. Okay, so the next step is you're going to set up a grid and write the given or the known over 1. So I have my grid set up, and my known is this side right here, right? It's got a unit here and a number, which means we know something about calcium nitrate. So 243.67 grams CaNO3 over 1. And now we need to write out our equality or our conversion factor that relates the units given in the problem. And remember, we are using the equality 1 mole equal of something, in this case CaNO3 equals the molar mass of CaNO3. So while we're here, why don't we try to calculate the molar mass of CaNO3? So the first thing we need to do is figure out how many of each atom we have, right? So we have 1 calcium. This number here, the 2 on the outside of the parentheses, distributes, which means we have 2 nitrogens and 6 oxygens. And the molar mass of calcium is 40.08 molar mass, right, a mole, grams, and 14.01 grams for our nitrogens, and 16.00 grams for all of our oxygens. And when we add all of this up, we come up with 164.10 grams. 10 grams because we're adding, and each of our atoms has 2 digits after the decimal. So if you remember, we're trying to find our equality, so our equality is going to be 1 mole of CaNO3 equals the molar mass of CaNO3, which we calculated as 164.10 grams of CaNO3. So we've now written out our equality or conversion factor that relates to units given in the problem. Really quickly for clarification, our units here are mole and grams. And if we go back to our original math problem, you will see that our units here are grams and moles. Okay. So the next step is to put the conversion factor into the grid, and this is the important part. You need to set it up so that all the units cancel out, and then we'll solve. All right, so how are we going to set this thing up? We need to take one of these numbers, one side of the equation or the equality, and it needs to go on the bottom side of the grid, and one needs to go at the top. How do you decide? Well, you want your units, again, to cancel out. So, since we have grams up here at the top, we want grams down here at the bottom, which means we are going to be using the right side of the equation for this one, 164.10 grams CaNO3 2, which means on the top we'll go 1 mole CaNO3 2. And now an important step is to make sure we actually did set this up right. Do these grams CaNO3 2 cancel out with the grams calcium nitrate down below? The answer is yes, they do. So now what we need to do is grab our calculators and do some calculations. Okay, so what we're going to do now is we are going to multiply across the top, and then we will multiply across the bottom, and then divide our answer. So when we multiply across the top, 243.67 times 1 mole CaNO3 2, we end up with 243.67 mole of calcium nitrate divided by 1 times 164.10 gives us 164.10. Now we divide 243.67 mole calcium nitrate divided by 164.10, and that gave me 1.484887264 mole calcium nitrate. And the last step is our sig figs. Because we were multiplying and dividing, we will be looking for sig figs, or the number that has the least number of sig figs. And I should make a big point here. This 1 mole is not a measurement. It is not used for sig fig calculation. We only use our measurements, okay, which includes things off the periodic table. So if we look at this number here, we've got 243.67. That is a total of 5 sig figs. And this number down here is a total also of 5 sig figs. So our answer also needs to have 5 sig figs. So that would be 1.4848. Those would be our 5 sig figs. So the first number we're going to drop is this 8, which is 5 or bigger, which bumps that previous 8 up to a 9. So our final answer will be 1.4849 mole of calcium nitrate. There you go. So hopefully that didn't look too difficult. If you take it step by step, you write everything down, including the units and the atom or the molecule, cross stuff out. This is not that bad. Okay, let's try a couple practice problems. If you think you feel comfortable trying this on your own, then hit pause, try it on your own, hit play, and see how you did. If you don't feel comfortable yet, watch this one, then hit pause and try the next one on your own. Okay, so how many moles are in 92.2 grams of FeO3? Fe2O3, sorry. Okay, first step, turn this into a math problem. So we know we have 92.2 grams of iron 2O3, and we want to know what that is in moles. All right, now we're going to draw our grid and put our known, which is this one, into the grid. 92.2 grams Fe2O3 over 1. All right, next our equality. We've got grams and moles, and it's grams of Fe2O3, right? So we're going to use the equality, 1 mole Fe2O3 equals the molar mass of Fe2O3, which we need to calculate. All right, so we have irons. We have 2 of them, correct? And the molar mass of iron is 55.85 grams. And remember, I got this off the periodic table as the atomic mass, but because it's a whole mole of them, the unit's going to be grams. And there are 2 of those guys. And then we have oxygen. There are going to be 3 of those. And the molar mass of oxygen is 16 grams. And I'm going to run out of space. Okay, so now we just need to add this all up. And I got 159.7 grams Fe2O3. We have to look at sig figs, or in this case, because we're adding, we need to look at decimal places, and all of our numbers have 2 digits after the decimal, and so that means I'm going to need to throw a 0 in right there. So my equality is now 1 mole of iron 3 oxide equals 159.70 grams of iron 3 oxide. Now we need to take our equality and put it in the grid, putting 1/2 of it on the bottom, 1/2 at the top. And because I have, oops, I didn't want to do that. Because I have grams at the top, I want to put grams at the bottom. So I have 159.70 grams of Fe2O3 on the bottom and 1 mole of Fe2O3 on the top. Now let's check to make sure we set things up right. Do grams Fe2O3 actually cross out grams Fe2O3? The answer is yes. So all we have left to do is to actually get out our calculators and solve. So when we multiply across the top, meaning that with that, we end up with 92.2 mole Fe2O3. And when we multiply across the bottom, we end up with 159.70. When we divide 92.2 divided by 159.70, come up with 0.577332498. I'm out of room. Mole Fe2O3. And now we need to go back and look at sig figs. So this number here has how many sig figs? He has 3 sig figs. And this number here has, it looks like 5 sig figs. So our answer needs to have 3 sig figs. That 0 is not significant. It's just a placeholder. So we'll be keeping the 577. Since we're dropping the 3, and because it's less than 5, we just drop it. So our final answer is 0.5 0.77 mole Fe2O3. Okay, so I have one more practice problem for you, and I highly suggest you do it because it's set up slightly different than the other problems. So why don't you hit pause, solve the problem, and then hit play and see how you did. All right, so the first thing we need to do is set up the problem as a math problem. And so we end up with 3.32 mole K2CO3, or potassium carbonate, equals X grams potassium carbonate. Next, we're going to write the grid and put in our known over 1. And we're going to write our equality with the units mole and grams in it. So we will have 1 mole of potassium carbonate equals the molar mass of potassium carbonate, which we do have to calculate. And so we know we have 2 potassiums, a carbon, and 3 oxygens. So the molar mass of potassium is 39.10 grams, and there are 2 of them. The molar mass of carbon is 12.01 grams, and the molar mass of oxygen is 16 grams. Let's try that again, plus 16.00 grams. So now we need to add that up, giving us 138. Oh, didn't do that right. Giving us 138.21 grams of K2CO3. Although before I commit too far, I should double check my sig figs, or because we're adding, in this case, digits after the decimal. And they all have 2. And if you haven't noticed by now, most of the atoms on the periodic table have 2 digits after the decimal. So our equality is 1 mole of potassium carbonate equals 138.21 grams of potassium carbonate. Okay, so let's see where we're going to put what. We have moles on the top, which means we are going to put moles on the bottom. So we will have 1 mole K2CO3 on the bottom and 138.21 grams of potassium carbonate on the top. Let's double check that we did this right. Mole K2CO3 crosses out mole K2CO3. And so from here, we just need to solve. All right, so when we multiply across the top, I came up with 458.8572 grams of K2CO3, and when we multiply across the bottom, 1 times 1 equals 1, so we don't really have to do too much in the way of dividing, so let me just get rid of that stuff. So there's our answer, almost. We still need to figure out our sig figs, right? So this number has 3 sig figs, and this number has 5 sig figs, so our answer is going to have only 3 sig figs, which is the 4, the 5, and the 8. So the first number we're going to drop is the 8, which is 5 or bigger, meaning we need to round up. So that means our final answer is going to be 459 grams K2CO3. All right, there you go. We're done. See you tomorrow.